Good afternoon and welcome to Paging All Windows Geeks, Finding Evil in Windows 10 Compressed Memory by Dmitry Antonov, sorry about that, Omar Sardar. This is the last session of the night, of the conference, so enjoy and do please turn off your phones. Thanks.
All right, thank you, Kevin, for that awesome introduction. So my name's Omar, this is Demeter, and we're reverse engineers on FireEye's Flare team. That's short for the FireEye Labs Advanced Reverse Engineering team. So we're going to be talking about finding evil in the Windows 10 compressed memory today. So before we get started, let's do a quick show of hands. How many people here are in the DFIR community? Raise your hands. Okay. How about reverse engineers? How many of those do we have? Okay, and finally, endpoint developers, kernel developers, etc. Awesome. Okay, so that's like a 2 to 2 to 1 ratio. I'll assume the 90% of you that didn't raise your hands are management, so sounds about right. Anyway, so that's great news, and I believe that we have something for all of you in this presentation, so let's get started. Long story short, the Windows Memory Manager has changed a whole lot between Windows 7 and 8, and then again between Windows 8 and 10. Some of these changes have actually disrupted forensic investigations. So like those of you who have used volatility on Windows 10 machines, you might have found that you're missing a lot of data that you may have expected to see. And as expected, you don't know what's lurking in what you can't actually extract. So let's go ahead and fix that today. My name's Omar Sardar. I'm a staff reverse engineer on the Flare team. My job is basically to reverse engineer malware daily and to reverse engineer accurately. I'm involved in automating reverse engineering as well as a niche role of analyzing Windows internals for product. So anytime a forensic artifact of some sort changes between Windows versions, I'll crack open the Windows kernel, figure out where it is, and write up a proof of concept for our product team. That'll get rolled into our product, and FireEye will have the latest forensic artifact detections. After 5 p.m., I enjoy biking, making pizza, drinking espresso, and of course, beer. You can catch me on Twitter at osardar1.
Hello, everybody. My name is Dimitar Andonov, and I'm a senior staff reverse engineer on the Flare team. I reverse malicious software on a daily basis, and I'm particularly interested in bootkits and rootkits, so I try to take those tickets when I see them in the queue. Part of my job is to analyze Windows internals for FireEye products. As Omar mentioned, when certain forensic points of interest change with the operating system, it's our job to hunt those changes down and help the engineering teams. In my free time, during the winter, you can find me snowboarding on the slopes of the Rocky Mountains. And a part of that, I play video games, enjoy quality espressos, and socialize with friends over an IPA or two.
All right, thank you, Demeter. So why don't we start off with story time? Let's rewind the clock back to 2016. It was another awesome day on the Flare team, just crushing one malware sample after another. And my boss, Josh Homan, gave me a call. And this is great for 2 reasons. 1, it's not my daughter's daycare. And 2, also because I work in isolation, so any call is really nice. I could practically feel his hair on fire as he told me about how customers using our endpoint audits tool were actually unable to extract Windows 10 memory images and actually conduct any sort of forensic operations. And in fact, it turned out everyone was really failing. We found out that volatility, recall, redline, memorize, all of them weren't really doing a good job with Windows 10. So it became my job to investigate this issue. And they have a saying that when you're a hammer, everything looks like a nail. Well, when you're a reverser, everything needs to get dropped into IDA Pro. So I closed out my malware ticket, cracked open the Windows 10 kernel, and started reversing. So this presentation today is the result of that analysis, as well as the integration into volatility and recall, along with some other tools, so you don't have to go through this effort. Okay, so I'm going to start this talk off by running through the memory manager really quick, the Windows Memory Manager, and that's to lay the groundwork so we can actually understand some of the updates that were made in Windows 10. At that point, Demeter will take over and talk about the undocumented store manager structures used to actually access compressed memory. I'll take over, and then we'll roll into how we can go about automating that analysis so we don't have to actually reverse each and every kernel that comes out. At the end, for the DFIR community, I'll go through volatility and recall, and I'll do a lot of before and afters so you can see how this integration can actually impact your investigations. Realistically, we're going to be flying in hot today, so we'll take Q&A in the speaker wrap-up room, but we'll see how we end up. Okay, so brief overview of the memory manager. Anytime you launch a process in Windows, that process gets anywhere between 2 gigabytes to 128 terabytes of memory to work with. A lot of that just depends on your Windows configuration, as well as which version of Windows you actually have. It's the memory manager's job to translate that virtual memory back into physical memory. Physical memory just refers to memory that's on your RAM, like the sticks of RAM in your laptop. The memory manager is also responsible for moving data to and from the hard drive, and that's an operation that we call paging. Out paging is when you go out to the hard drive, in paging is when you come back in. On top of that, a whole lot of bookkeeping happens, and a lot of that bookkeeping is just there to support performance optimizations. Okay, so I mentioned that virtual memory exists. So let's say I'm a 64-bit process running on a Windows 10 machine. I'm going to have 8 terabytes of memory to work with. Now, I don't know about your laptops, but I definitely don't have 8 terabytes of memory for each process that I run, let alone all of them. So that 8 terabytes of memory is what we call virtual memory. Anytime you want to access data within that virtual memory, all you have to do is know what address you want to read it in from. And the memory manager will return data back to you in hex 1000 byte swaths of memory. And that's what we call a page. So the location of the actual data that you have is completely transparent to notepad.exe. It doesn't matter if it's in RAM, it doesn't matter if it's on the hard drive, or really anywhere else. So let's say me, Omar.exe, has gone ahead and made a request to the kernel. I say, hey, give me 1 megabyte of memory to work with. The kernel and the memory manager will respond back to me. And in this case, the kernel said, okay, Omar, hex D1A746 followed by some zeros. You can work with that address. Now, that address might look like a series of random numbers, but it's actually not. You can break it out into a series of 9-bit indices followed by a 12-bit offset. Each of those indices can get plugged into what we call a series of page tables. So by plugging in these indices and navigating through the page tables, we ultimately arrive at what we call a series of page table entries. Now, there's all sorts of different page table entries. There's 64-bit data structures, but really at the end of the day, they're just markers that let the memory manager know where to actually go to find the page. There's all sorts of different types of PTEs. For example, a subsection PT just corresponds to a memory mapped file. There's a hardware PT for memory that's in physical RAM. And then there's a software PT. That's the one we're going to be interested in today. The software PT signifies that your data has been outpaged. So let's say we go through, we navigate through all the page tables, and we ultimately arrive at a software PTE. We're going to be interested in 2 of the fields here today. There's page file low and page file high. Page file low is just an index from anywhere between 0 to 15. 0 traditionally corresponds to pagefile.sys, and 1 corresponds to swapfile.sys. Page file high is just the offset that you need to jump to within that specific page file to actually locate your data. Now let's go ahead and switch over to the Windows debugger. I'm using the PTE extension here on what's probably a random address. So you can see Windows debugger now. It goes through and traverses the page tables for us, ultimately arriving at the 64-bit PTE. It displays that for us, along with some other information that came from the software PTE structure. For example, we can see that our page file index is 2, and then our offset is actually hex 17A4D. Now let's do a quick recap of where we're at. Let's say I'm notepad.exe and I need to resolve some data. No problem. I'm going to walk through the page tables, ultimately arriving at a PTE. Remember, the PTE is just a placeholder for where my page is actually located. If it's a hardware PTE, I'm going to reach down to physical RAM and grab it from there. If it's a software PTE, I'll fetch my page from the hard drive. I'll ultimately update the PT to reflect that my data is now back in RAM, and then Notepad will get the data at the end of it. So this is what we call the demand paging model. The model has actually changed a lot over time in ways that include performance optimization. A class of performance optimization revolved around keeping data away from slower media like the hard drive is a major class of them, and memory compression falls in that category. So for those of you with Windows 10 machines out there, you can actually open up your task manager and head over to the performance tab. And there you'll actually see how much of your memory is compressed away. So eyeballing this, it looks like about 10% of the system's memory is compressed away. So as someone in forensics, you wouldn't have had access to this data until now, along with other data that relied on data that had been compressed away. So you might be thinking, like, is it really worth all this effort to compress just 10% of the system's memory? And well, you're totally right. It actually is a lot of work. But it turns out that accessing data from your hard drive is a very, very slow operation. It can be an order of magnitude slower than pulling it in from RAM. So to leverage this, modern operating systems actually compress their memory so they can use as much RAM as possible. In 2013, Linux started doing it with the ZSwap project, Mac OS rolled it in, and that's actually right around when Windows rolled it in as well. So it seems like a lot of work, but memory compression is actually a really fast operation nowadays. We have really fast CPUs, so the trade-off ends up actually being worth it. And having a tunable system from which we can maximize RAM storage also allows for really flexible kernel development. Who here knew that the same Windows kernel built to run on an enterprise server is the same Windows kernel that runs on your mobile phone, or used to? Okay, so I've gone ahead and dumped out the page files here using the virtual memory extension in WinBag. So we see that index 0 corresponds to pagefile.sys and 1 corresponds to swapfile.sys. But what about this mystery second file? Where can we go to actually learn more about it? So it turns out that the memory manager actually has a structure called paging file. The structure is used to represent traditional page files, like pagefile and swapfile.sys. As of Windows 8.1, the structure has now been extended to actually support what we call virtual stores. You can check the virtual store page file Boolean value for confirmation that your page file is within the virtual store. To actually find an array of these page files, you can head over to the memory manager's paging file export, and you'll find a list of pointers there that points to each of the page files on your system. Unfortunately, in Windows 10, that's no longer an export. So if you're interested in locating that, just check out the white paper. We walk through that whole process. Okay, to make sense of the virtual store, we need to actually take a step back for a second and look at the store manager. The store manager is responsible for creating the virtual store. The store manager is responsible for storage allocation and content tracking with regards to all the performance optimization systems that happen in Windows. The store manager is capable of supporting encryption and compression, and with any data that it gets, it can add it to a store, fetch it, or just delete it from the store altogether. And when a page from the memory manager rolls into the store manager, it's called a store page at that point, and that page is represented by a store manager page key. As you've guessed, the store manager is ultimately responsible for supporting memory compression, along with all sorts of other cool technologies like Superfetch, ReadyBoost, and ReadyDrive. So any page that goes into the RAM-backed virtual store actually gets compressed with the Express LZ77 compression format. Now, all of this is subject to change, but that's what it's been since 2015. All these pages are actually stored in a minimal process, which is just a container called mem compression. I think you can actually see that in Process Explorer, or if you have the Windows debugger hooked up to the kernel. And don't forget, one page corresponds to a single store manager page key. So how do we go about actually deriving a store manager page key? So let's say we walk through all the page tables again, and then we arrive at a software PT. We're going to take a look at page file low and page file high. We're going to run through this small math operation here, effectively just smushing these values together into our store manager page key. For a more real example, let's say our page file high value is hex 17A4D, and our page file low is 2. We can run through that math operation, or we can just smush them together, and at the end of the day, we'll get a 32-bit value of 2001 7A4D. Now, all of this is undocumented, of course, and subject to change. So as of Windows 1803, March 2018, the algorithm changed just a little bit. The software PT structure got a new field called the swizzle bit. So the new algorithm respects the swizzle bit, and it says that if the swizzle bit is clear, you go ahead and move forward, and then you perform this operation here, very similar to the last one, and then you use the invalid PTE mask from another memory manager structure. Otherwise, you just use the algorithm that was previously specified. For more information on this, just check out the white paper. A lot of it's spelled out there. So just another example now using the Windows debugger. Let's say page file high is hex 26 EDF. The Windows debugger actually parses it and says, no, it's actually 24 EDF. So in this case, it checked out the swizzle bit and then updated the offset accordingly. So as a result, we get an SMK page key of 2002 4 EDF as opposed to 2002 6 EDF. Now you might be wondering, okay, so we have this store manager page key, but how do we actually go about getting our page back? So it turns out that the store manager page key is actually used along the way as we traverse a series of undocumented Windows 10 store manager structures. The store manager page key is used to derive metadata that ultimately helps you reconstruct the address of your compressed page within the mem compression process. On the left side, we have some structures that correspond to like the store manager as a whole, and on the right side, we have structures that focus on specific stores. All of that magic begins at the export called SM globals. So I'm going to go ahead and hand it off to Demeter at this point, who will take this into a lot more detail, and enjoy the ride.
Thank you. Thank you, Omar. So the next few slides are going to be a bit more technical, and I apologize for that. The content will be a little bit more drier, and I know it's after 5 p.m. on the last day of the conference, and you guys are probably tired, but I think it's really important to understand how do we get from the page key all the way to the compressed page in memory. What does it take? There are a lot of calculations involved in this process, and I'm not going to show them here because the presentation will become really dry. But we are releasing the white paper today along with a complete walkthrough. So if you want to see this in action, you can grab a kernel debugger or some other tool and follow the walkthrough. So without further ado, let's start with a more detailed overview of the structures involved in this traverse. On the left side, the yellow structures are global structures, and we call them global because they define all 1024 stores available in Windows 10 version 16.07 and later. The yellow structures also define the correlation between all the page keys on the system with their respective store. On the right side, the nested blue structures define one single store on the system. And the data inside is used to calculate the virtual address of our compressed page in memory. Currently, all the compressed pages reside inside a dedicated process called mem compression, and I will talk more about it in a few slides or so. So it looks pretty messy. How do we start with all the traversing here? Well, we all need to know two things. One is the page key, which we know how to derive. Omar showed us already. And the next piece of information is the address of the kernel variable known as SM globals. The value of the kernel variable holds the address of the first structure we need to traverse. Let's start the navigation through the global structures now. As I said in the previous slide, SM globals points to our first structure we need to start the navigation from. The name of the structure is globals, and it contains two nested structures called store manager and SMKM. The store manager exposes a global bit tree that correlates the page keys on the system with their prospective stores. The SMKM structure defines a two-dimensional array of store metadata elements. And each of those store metadata elements defines a single store on the system. We have 1,024 elements, 32 by 32. So how do we go about navigating these structures? Well, first, we need to find the bit tree and traverse it until we find our page key inside. What am I talking about when I mention that we need to traverse the B plus tree? Well, we will see this structure twice during our traversal, so let's go ahead and talk about it now. By definition, it's a B plus tree, which means all the data is stored in the leaves, and the non-leaf nodes contain ranges of keys. The top of the structure contains a pointer to the root node, along with a value that specifies the number of elements inside the tree container. Our first goal here is to dereference the root node, and that will get us to the first non-leaf node. Inside the node, you will see ranges of keys in increasing order. So our goal here is to find which of those ranges contains our key. When we find that, we will dereference the associated pointer, and when we keep doing that, eventually we will end up inside a leaf node. The leaf node will have all the keys associated with the metadata. In our case here on the slide, the key is associated with a store index and some flags. Let's traverse a tree with an example key. So we have the base of the tree shown, and we calculated our page key to be 2001B68F. So our first goal here is to find the root node. We dereference the pointer to it, and now we see ranges of keys along with pointers to the next nodes. Since our value 2001B68F is greater than 2001A210, but less than the following key, our range belongs to the second entry inside the node. By dereferencing the associated pointer, we will eventually reach the leaf node, and then we will see our key inside associated with the store index. And in our case, the store index is 0. Now, as we know how to traverse the B plus trees, let's get back and traverse those global structures. So far, we found that our page key correlates with a number, one number, which is 0 in the previous example. But what we need to do now is to find two indices, because SMKM array of store metadata elements is a two-dimensional array. So we need two indices in order to specify a specific element inside it. So how can we calculate those indices? Well, it turns out that the store index is a compound value. By dividing by 32, we will get the first index, and if there is a remainder, that will be the second index. In our example, store index 0 divided by 32 is 0, and the remainder is also 0. And now we specified the exact location of our store metadata structure in memory. The store metadata structure contains a pointer to the store we are after. Now, as we have the store selected, let's look at the structures that implement it. There are three major components of the store. The first component is the topmost structure called SMKM store. The most important element in the structure is a pointer to an array of pointers to regions of memory inside the mem compression process. The next component is called data manager, and among the other data, it contains what kind of compression algorithm has been used to compress the data, and also another bit tree that correlates the page keys of the store with a value we call chunk key. I will talk about the chunk keys in the next slide. And the last component is called chunk metadata. It's a nested structure that defines a two-dimensional array of chunks. Each of the chunks define a vector of page records, and each of those page records contains information about our compressed page in memory we're after. So let's see how we navigate those structures and calculate the virtual address of the compressed page we want to. We start the traverse with navigating the bit tree in the same manner I showed you in a few slides ago. That would allow us to find the corresponding chunk key. And the chunk key is a composite value. It contains three pieces of information inside. Two indices inside the chunk array, and also an offset within the chunk. So after decoding, we will be able to find the exact page record that corresponds to our compressed page in memory. Now the page record is another structure that, among the other things, contains the compressed page size, the CRC32 checksum, and also a value known as a region key. And as you can expect, the region key is another composite value that encodes the index into the array of pointers to regions of memory inside mem compression process, and also the offset within that region. If we are able to find and decode the region key, we will effectively know the virtual address of the compressed page. Knowing that address allows us to derive the PTE of the compressed page. And when we have the PTE, if it's a hardware PTE, so the valid bit is set, our compressed page will reside in physical memory. Otherwise, if the valid bit is not set, we will be dealing with a software PTE, and we will know that the data we're after reside in some page file. Both cases are trivial, so after we retrieve the data from the location specified in the PTE, we can decompress it by using the compression algorithm specified in the data manager structure. Okay, a few words about the container process. Historically, all the compressed pages were kept inside the system process. And that changed with the recent versions of Windows. Now we have a dedicated process, minimal process, known as mem compression. As minimal process, it doesn't have a process environment block, it doesn't have anti-DLL mapped, and no user threads are running inside. Additionally, all the user space is utilized as a storage for the compressed pages. The store management inside this process is implemented by several minimal threads that provide support for paging in, paging out data, for compression and decompression, and for allocating memory and deallocating memory. Currently, all the stores point to this process. But the store design is very flexible, and it allows every store to have its own dedicated process as a container. In theory, that means that we can have up to 1,024 dedicated container processes running simultaneously on the system. All right, before wrapping up the retrieval process, let me revisit the big picture Omar showed us before, but this time let's include the virtual store as well. So all starts with a process asking to access some virtual address. We know now that the virtual address is not a random value, and it could be parsed, and the indices can be used to traverse the page tables. Ultimately, we will arrive at a PTE that corresponds to the virtual address. That PTE, if it's hardware PTE, will specify that the data is in physical memory. If it's a software PTE, it will specify that the data is in the page file or inside the virtual store. In the latter case, we have all the information needed to calculate our page key out of the information inside the software PTE. With the page key and the value of the kernel variable SM globals, we will be able to traverse all those structures I talked about, and ultimately we will arrive at the virtual address of the compressed page in memory. Now at that point, we can calculate the PTE for the compressed page as well, and then if it's a hardware PTE, it will show that the compressed page is in physical memory. If it's a software PTE, it will specify that the compressed page was further evicted by the memory manager into some of the page files on the system. In both cases, we can retrieve the data, decompress it, and return it to the process. So that was all about how we retrieve a page from the virtual store, and I hope it wasn't too awful and you got the gist of it. For those of you who feel adventurous, grab a kernel debugger, read the white paper, and follow the walkthrough. Now Omar will take over for the rest of the presentation, starting with explaining how can we automate certain parts of this process. Back to you, Omar.
All right, thank you, Dimitar. So you might be thinking now, case closed, we know all the structures we need to actually access our data. Wrong. We're almost there though. So it turns out that these structures are constantly in flux. They're all undocumented. So we end up seeing new structures pretty often, and it was starting to drive me crazy, kind of like the slide. So how do we deal with these structures in flux? Well, one option is that we crack open the kernel anytime we want to actually analyze these structures. But, is that really enough, doing that every 6 months? Okay, let's break apart a version of Windows now. So over here, I have Windows 10.0. That's the major and minor version. I think that's pretty straightforward. And then we have a build and a revision. Builds are what we're used to seeing every 6 months, like 1703, 1803, etc. Revisions are like what we would see on a Patch Tuesday update, for example. So looking at this now, we would actually have a kernel potentially every week that would need to be analyzed. And even after looking at this for a while, it would still take me 6 to 8 hours to actually go through each kernel and verify that all these structures have changed. And ultimately, that's just way too many kernels. We need automated analysis. But how do we go about doing that? And then it hit me. Why not leverage emulation? So luckily enough for me, Tom Bennett there on the Flare team had been working on Flare Emu since, I think, 2017 or so. Flare-EMU is essentially the marriage of IDA Pro and the Unicorn emulator. It has loads of helper functions that help reduce the level of effort needed to actually leverage Unicorn within your projects. Flare-EMU loads binaries for you. It allocates memory automatically anytime you hit a fault. And then it has a very straightforward API for accessing registers and memory context. And ultimately, this enables rapid prototyping. So how do we go about using emulation to actually auto-extract these undocumented structures? So by this point, I had analyzed somewhere around 10 kernels by hand, and this was spanning like a 2-year period or so. And I'd actually discovered plenty of changes between these kernels, but I also had plenty of commonalities between kernels. So it turned out that the location that these structures were used generally stayed within the same class of functions. The function prototypes used also stayed the same. So in other words, fields or the structures themselves ended up being arguments to the same functions. If those weren't good enough, I could look at the order of operations. Sometimes data pulled in from a structure was accessed in a certain order, and that would remain constant. If that failed, I could look at how data was used. Maybe some math is run on some of the values that we pull out of these structures. And ultimately, that can help you figure out the field. And the last thing is, there's a whole bunch of processes running, and the call stacks generally remain the same. For me to run any sort of automation, I just needed one of these guys to be constant, and that was good enough. So why don't we try our hands at a real example here? RTL decompress buffer is at the end of the line in our page retrieval process. Demeter mentioned that the page was stored in mem compression and that we would pull it out of there and then decompress it. Well, this is where that actually happens. So let's go ahead and try our hand at automating the first argument going into it. That first argument, as we can see, is the compression format. Normally it would be express LZ77 here. Now let's backtrack a bit, and we can actually see that it comes out of the ST data manager structure. So unfortunately, when I open up a new IDA Pro database, that's not really what I see. I see something like this, EDI plus hex 220. So I know that EDI refers to the data manager from all my previous analysis, but how do we actually automate that hex 220 in a script? Well, one option is you can create a unique non-repeating pattern using Flare-EMU. You can just load that up into the ST data manager structure. I think a lot of people here are familiar with techniques like this, like in shellcode crafting, for example. So at that point, we can let Flare-EMU run, and then we can just view the context and specifically view the stack after we've run Flare-EMU and look for what we expect to see. So I see all sorts of arguments into decompress buffer, but I also see that the first argument, or the compression format, is now KM. KM is obviously not a valid compression format, but since we preloaded the data manager structure with this, we know that it's going to be somewhere within our pattern. And sure enough, there it is, right at the bottom. If I wanted to write a simple Python script here, I could just search for that pattern, and sure enough, hex 220. Let's go back and cross-check. Yes, it's at hex 220. The compression format is hex 220 off from the base of the data manager structure. So ultimately, simple techniques like this, along with a whole bunch of other ones, were used to ultimately derive all the fields that we required for page decompression. The script dropped my analysis time from 6 to 8 hours down to about a couple minutes or so, and it let me focus more on code updates and testing out our in-house driver. So if you're interested in the script, reverse engineers in the room, you can check out my Twitter afterwards, or there's like a URL at the end of the presentation. This is effectively going to be your guide into figuring out where all these store manager structures are actually located. So for the rest of us here, we might be thinking now, well, that's fantastic, Omar, but what am I going to do with a bunch of offsets? I can't walk through memory dumps each time I want to extract a page. And that's perfectly valid criticism. So this is a quote from Andrew Case, Volatility Core developer back in 2015. Ultimately, it says the inability to access Windows 10 compressed memory has really been one of Volatility's as well as Recall's biggest problems. Without access to that compressed memory, we lose visibility into forensic data that we'd expect to see, like simple DLL lists or driver lists. So at this point, given that the community heavily relies on tools like volatility and recall, it only made sense to integrate Flare research into there. Blaine Stansel, who previously presented with me, actually wrote the volatility plugin, and Sebastian Fogel wrote the recall plugin. The primary goal in writing these plugins was to actually integrate all this research in a transparent manner. We didn't want end users to have to deal with the mechanics of all these store manager structures. So to start, we created a plugin. So the product was the ability to feed it a virtual address of a compressed page. The plugin analyzed the PTE to determine if the target page was located in the compressed store. And then if so, it would pump it through all the structures that Demeter previously described. Finally, we would get the page and then decompress it and return it back to the user. So let's take a look at this plugin, this initial prototype in action. I have this process, rammeter.exe, and we have a marker page located at hex 7C followed by some zeros. Previously, it was unreadable. Now, with the Flare research integration, we actually have real data coming back. So the next step here is, we have the plugin running, but existing volatility recall plugins can't leverage another plugin that's on the system. So we have to sit lower on the stack here. So that involved converting all this research into what we call an address space. With the ultimate goal of transparency, when we functioned as an address space, we were able to load most volatility and recall plugins, and you'd be able to use them as expected. This is a pretty big win for the DFIR community, but let's take a look at some actual real-life examples here of why this is important. Let's take modules, for example. This just walks through the kernel and lists some drivers that are loaded. Without the Flare research integration, you're actually missing out on some drivers. You're potentially missing out on a bad rootkit that hasn't unlinked itself. Otherwise, with the Flare research integration, everything is there as expected. Now, DLL list, this was a pretty bad one. So without the Flare research, we couldn't even get the command line, let alone any of the DLLs that were loaded by our process. And this is subject to change depending on what's compressed and what's not. But with Flare research, you can see that's all back, where it's supposed to be. Driver scan, very similar to modules. It just scans for driver objects, applies some heuristics in memory. Previously, we were missing all sorts of data. That was data that was sent out to the virtual store. With the Flare research, as expected, it's all there. Now, I don't want to harp on this for too long, but we can look at the hash dump utility. And previously, we couldn't get anything. But now we can actually extract and decrypt cache domain credentials. Okay, so that's a lot of fun. But all I really showed us was that we were able to get stuff that we previously had access to. Now, why don't we take a look at a real-life sample? So I reverse engineered the sample about a couple months ago, and it made a pretty good candidate. So I went ahead and rolled it in here. So let's walk through it. The malware is an exe, which then loads a DLL, which then loads shellcode from the disk, which then loads reflectively loads another payload. That payload then reads more shellcode off the disk, which then loads another payload. And then that payload reaches out to the C2 server. I know this is very excessive, but I don't actually know the malware author, so it is what it is. Without the Flare integration, we'd go through, we could do a process listing. Format options didn't have any parents, so that seemed kind of sketch, so we looked into that. And there, we actually see that even without Flare research, we do get a DLL listing. Certain memory hasn't been paged out, so we're lucky this time. We have access to it. We can actually extract a couple of mutexes as well. I see will staging 2, check and protect process thread, and that's not so bad. Unfortunately, that's where my luck ended. Malfind couldn't work. I couldn't actually get any file handles. Proc dump and DLL dump didn't work. But in volatility's, to volatility's credit, these were subsection PTEs, and they actually corresponded to files on disk. So if I had access to that, I would have been able to carve them out. And then finally, bad dump didn't work either. So what to do? Okay, quick recap. The exe and the DLL have been, are on the hard drive, but I wasn't able to find any of the shellcode. I wasn't able to find any of the reflected payloads. So if you're facing the C-suite right now, this is a position you really don't want to be in because you're probably not coming back. So let's go ahead and integrate Flare Research now and see what we get. So it looks like a new mutex has shown up. It's pretty nice. I can see that we actually have a handle to another format options file. That's pretty good. Frankly, not that exciting though. Let's take a look at malfind. Malfind, on the other hand, has carved through the process. It's gone through all those pages that we've decompressed, and it's found a few with the read, write, execute permissions. I think all the reverse engineers in the room can immediately identify this as shellcode. These are the two shellcode files that had been loaded into memory. Next up, I think everyone in the room can identify the MZ header, telltale sign that you're dealing with the Windows binary. And this had been loaded also with page read, write, execute permissions. These are our reflectively loaded payloads now. Let's analyze some of these payloads a little more closely. So just by looking at this, I think we can figure out that we're dealing with the server DLL. The malware author went ahead and left some PDB information in there. If that wasn't enough, you can just look at some of the strings below that, and it should be pretty obvious that we're dealing with a C2 DLL. If we look at the other payload on the left side, we see some sandbox evasion. Down the middle, we see some system triage. And then we see those mutexes, so we now know where they originated from. But we also see this cool network-based indicator. We see cellaware.net. So, we'll shelf that. We'll come back to it later. So now, with the Flare Research, what do we have? EXE and the DLL aren't coming back unless we can reach the hard drive, but that's okay. We now have access to both shellcode payloads as well as the reflectively loaded payloads. Now, on the Flare team, we have all sorts of cool, interesting systems that perform advanced reverse engineering efforts for us. So we go to Google and we plug in these network indicators. And as you can see, the first result here was actually just a Yara signature. If we check it out, we see cellaware.net followed by a FireEye APT30 report. It looks like the sample is potentially being used in APT33 and beyond. For those of you who caught it, we just dropped the APT41 report yesterday. Might be worth checking out. All right, so thank you very much. I'm Omar. This is Demeter of the Flare team.
Thank you.
For those of you who are interested in reverse engineering and pursuing this line of work, check out the Flare-On competition. We go live next week, and I believe we already have a challenge up. Now, for the actual source code involved with all this, I guess all the good stuff, head over to github.com/FireEye. There's a volatility and recall repo. For the reverse engineers, you can check out all the automation work here. And if you're interested in automating some of your own analyses, check out Flare Emu as well. If you're interested in diving into way more documentation than that's needed, we have 3 blog posts up as well. They all went live today, as well as a white paper that goes really, really in depth. All right, and we got some credits here. Thank you for everyone who was involved. All right, looks like we have about 2 minutes left.
Thank you.
All right. All right, so I guess we have 2 minutes for questions, if we want to do that. Okay, so the question I get the most is, Omar, where did you get all these awesome emojis? These emojis come from the Microsoft emoji pack, with the exception of one, which came from the Twitter emoji pack. So now that we got that question out of the way, any others? All right, thank you, everyone. We appreciate it.
We will be in the wrap room if anybody wants to ask us.